So you get your AC power, and then all of the controls run on 24 volt DC, all right? And 24 volt DC is the nominal control voltage in industry, right? When you see 12 volts being used, it usually means it had something to do with automotive. And the lower voltages like 5 volts and 3.3, those are voltages used in small electronics like Arduinos and things like that. The problem with those low voltages is that they're very susceptible to electrical noise. So you have to be really careful about isolating things so you don't have trouble with crosstalk. Anytime two wires run next to one another, parallel, there is some electrical interaction between them, okay? So as a result, we try to keep the power wires, especially the AC, because the AC current is flowing back and forth, and anytime a current is passing by a piece of metal, it transfers some power into it. Right? DC doesn't do that. Two wires DC laying next to one another, there's no interaction. AC next to another wire, there will be power induced in that other wire. Very tiny, but it happens. Okay. So when we lay out the panel, we try to keep the wiring away from the higher voltages away from the lower voltages, and the AC away from the DC. So you can see that we came in with power up here, and all of this is AC, and then this AC comes out and goes down and comes down here to these contactors to go to the motors, but it doesn't go past the PLC. And this particular PLC has inputs, things that connect to sensors and stuff on the bottom, and it has outputs are all along the top. So the outputs come out, and they run things that coming out the bottom here, okay? And those outputs are, generally speaking, the outputs from PLC pretty much stay in the panel, all right? Because these outputs go to these VFDs. These are motor controllers. And so an output goes right from here to here. So the wiring's very short. That's the goal, is to keep the wires short and to keep them from like crisscrossing. Now I have no choice but to crisscross here, but by making the wires real short, it helps. Then so the other part of the outputs here come down and operate these contactors. And all the contactors have 24 volt DC coils. Now, if you get to running using big contactors, sometimes you have no choice but to jump up to 120 volt AC and work it that way. But when we do that, we usually add a relay. So a relay is another electrically operated, it's like a contactor. It's got one set of, this particular one's a single pole. It's got one set of contacts, and it's operated by 24 volt. And we would add this, and it would be called an interposing relay, okay? An interposing relay is just a way to allow a low power device like a PLC to switch a bigger voltage so they can switch a bigger contactor, okay? And so that's a common thing. And we have also some relays that are safety relays, which are the safety relay. The contacts aren't just like spring loaded. They have like a wedge that goes between the contacts. So when it shuts off, it positively breaks the contact. And those are safety relays. And those get used in conjunction with the e-stop. So like when we have door switches and stuff like that, we will have safety relays that go to the door switches. And this job will have some safety relays in here that because this will have doors, sliding doors, and we have to make sure the doors are shut before they can run the machine. So the relays, again, same story. They snap onto the rail, right? DIN rail makes it great because you can just add that. So again, I try to keep the wiring, the input wiring is, the inputs are all over here, the outputs are all over here, and the two don't cross. And that's a way of keeping the noise out of the system.